All right, guys, this is our lesson on acoustic resonance. So, this is how kind of a bit of the math and physics on how any instrument would work that involves tubes. So, the lowest frequency that an instrument can vibrate at is called the fundamental frequency, or also known as the first harmonic, and we call it F0. Higher frequencies than it can vibrate at are integer multiples of that fundamental frequency, so 2 times, 3 times, etc. And they are often called harmonics or overtones. Like mechanical resonance, the instrument is tuned to a particular natural frequency being that fundamental frequency. Standing wave patterns have a node at any closed end and an antinode at any open end. So when you think about a wave, and I'll just draw it like this for now, and you can picture just a wave that if you plucked a guitar string or something like that. So these spots that are at the zero line, those are called nodes. And these maximums and minimums are called antinodes. All right. So the maximums are antinodes, and then these spots, these dots I've drawn, these 4 dots are called nodes. Okay, those are spots where, they're called nodes. We'll leave it at that for now. So basically, you can set up any tube that you're given. Actually, I can write that in nodes 1, 2, 3, 4, and then the other ones are called antinodes. So, for a standing wave pattern in a tube, there always has to be an antinode at one end and a node at any closed end. So let me give you an example. So here's a tube that's open at both ends. So if it's open at both ends, then it has to have this antinode, this open spot, the open part of the wave at both of those open ends. If you were to close the air tube off in both ends, then it has to have a node at both of those closed ends. And then finally, if we had closed at one end, it's got to have a node at the closed end, and it's got to be open at the open end, a pattern like that or something. Or, well, any pattern really that you can imagine that follows that rule of a node being there, something like that would work. And then it's got to be open at the open end. So we'll start with the first 3 patterns for an open air tube, okay? So wind instruments, all they are is elaborate air tubes, and you just set up a standing wave and you hear a note. So the first resonant length for an open air tube means open at both ends, is going to have that antinode, that open part at both ends. And if you think about how much is in a wavelength, if you think about back to our intro lesson, each of these would be a half of a wavelength. So what you're looking at there is just one of these and one of these. So that's going to equal a half of a wavelength. This is a quarter wavelength, and this is a quarter wavelength if you compare it to the very first diagram we did in Introduction to Waves. So it's got a half of a wavelength. You can completely ignore the 512 hertz. That has nothing to do with it. I'm trying to teach you what the patterns look like, the standing wave patterns in these air tubes. So that's called the first resonant length. And then the longer lengths are just longer patterns that happen to follow that rule where it's open at both ends. Watch what I'll try and show you what I mean. Erase this at the top. So the next, or the longest pattern, or the second resonant length, is going to have the standing wave pattern that again is open at both ends. The third resonant length is again going to be open at both ends, and it's the next longest wavelength. Again, the 512 hertz has nothing to do with this other than you're using the same frequency to vibrate each of these air tubes. So this is a half of a wavelength, and this is again a quarter and a quarter. If you add that up, it equals 1 wavelength. Again, here we've got a quarter wavelength, a half of a wavelength, a half of a wavelength, and another quarter of a wavelength, and it makes 1.5 wavelengths. All right. What you guys need to know is just first, second, third wavelength, how to draw them, or first, second, and third resonant length, how to draw them, and how many wavelengths are in each: 1/2, 1, and 1.5. We're going to do the same thing now for a closed air tube. And a closed air tube doesn't mean closed at both ends. It means closed at one end. So again, just like on that slide previously, it's got to have a node at the closed end and it's got to be open at the open end. So the simplest, shortest pattern that you can draw has 1/4 of a wavelength. Again, the next two got to be closed at the closed end and open at the open end. That's going to be 3/4 because you've got that same quarter wavelength there and you've got the half wavelength here. 512 hertz, doesn't matter. Second resonant length and 3/4. And then finally, I don't think I need to draw this out for you, but there's a quarter, there's a half, there's a half. That's going to be 1 1/4 wavelengths. Now, I hope if you've been pausing this and kind of thinking about it as you go through, that you're realizing that what's the difference between this resonant length and that resonant length, and then this resonant length and that resonant length. And by that, I mean this one's 1/4 of a wavelength long, this one's 3/4 of a wavelength long, so that's a half wavelength difference. 3/4 of a wavelength to 1 1/4 wavelength, that's a half wavelength difference. Notice when you're going up a resonant length, all you're ever doing is adding a loop. And loops are half of a wavelength long. Let me go back to the previous slide and just show you again. Half of a wavelength to a full wavelength, difference of 1/2 wavelength. 1 wavelength to 1 1/2 wavelengths, difference of half a wavelength. When you're going up resonant lengths, one by one, the distance between two loud spots, and that would be resonant lengths, is equal to 1/2, not of a question mark, of a wavelength. All right, the distance between, and that's what you'd actually hear. So I've got these instruments in class where you just change their length, right? So when I hit the loud spots, I know I've hit resonant lengths. So if I hit 1, 2, 3, the first three, then I know I know that they're a half wavelength apart anyways. Let me show you how to do this in real time. So if we were doing a test on this today, this would be a good inquiry question. So the following is a list of lengths in a resonance tube where loud sounds were heard. So this involves lengthening the tube, and you hear a loud sound at 10, 31, 48, 60, 79, and 100 centimeters. You used a 1000 hertz tuning fork to make this happen. It says calculate the wavelength and velocity of the sound. So the loud spots themselves don't really matter. It's the distance between the loud spots that will help us find the wavelength. So 10 to 31, that's 21 centimeters. 31 to 48, that's 17. That's 12, that's 19, and that's 21 again. So would you say these experimenters did a very good job? I would say no, because the distance between loud spots is supposed to be consistent. So the 21, the 17, the 19, and the 21, you could say that those are good numbers, but then the 12 in the middle is a little off. The next thing you do in trying to find the wavelength is you find the average. All right, if you were doing an experiment, if you're doing it as a regular kind of knowledge-based test question, I would just give you the distance between loud spots and you would just go from there. But since this is an experiment, I've got 1, 2, 3, 4, 5 distances between loud spots. So that's going to get me the average distance between loud spots. I'm going to include the 12. If this was your experiment and you asked, should I leave out the 12? I might say, sure. But I think this gives me a pretty good average of 18 centimeters as distance between loud spots. And what did that last slide say? It said the distance between loud spots is equal to half of a wavelength. So to calculate the wavelength, I'm going to say wavelength, or rather half of a wavelength is equal to 18 centimeters. So that means the wavelength is equal to 36 centimeters. Done. All right, it's as easy as that. Students struggle with this usually because this comes at the end of the semester and maybe you run out of gas, but it's really quite easy. Just find the distance between the loud spots, find the average, and then double it. Essentially, that's the wavelength. All right, so that part is done. We found the wavelength. It also says find the speed of sound. So then we turn to the wave equation, B equals F times lambda. This was a 1000 hertz tuning fork. Not fixing that. 1000 hertz, and we're multiplying it by 36 centimeters, but I'm going to go 0.36 meters, I think, because I would like my speed to be in meters per second. So I go 1000 times 0.36. I probably shouldn't have needed a calculator for that. It's 360 meters per second. Often I'll have a part B that says find the temperature of the air in the room. Then we'd have to use our temperature equation, the 332 plus 0.6 times T, and that would get it done. What do we got here? A couple more examples. Air column, open at both ends, 1.5 meters long. A frequency is heard resonating from the column. Okay, of course there is, otherwise we wouldn't be doing this. What is the longest wavelength and its frequency? So again, finding wavelength and frequency that could be responsible for this resonance. So open at both ends. This is where you have to be able to draw this pattern, all right? The longest wavelength is always the fundamental frequency. So it's the first pattern, okay? The first resonant length is going to be the longest wavelength that you can hear. So this length is 1.5 meters, and the pattern is going to look like that. How many wavelengths is that? Go back to your diagrams. This is a half of a wavelength. So a half of a wavelength equals 1.5 meters. So that means the wavelength in this case is 3 meters. Done. So in this case, instead of saying where the loud spots are, all it told you is that the column is 1.5 meters long, and that it's the longest wavelength, which is the fundamental frequency. And then for the other part, for finding the frequency, again, I'm going to lean on this V equals F lambda, I think. Yes. Because it says that the speed of sound is 345 meters per second. Wants me to find the frequency, and now we know that the wavelength is 3 meters. So 345 divided by 3, I think, is 115, but I didn't punch it into my calculator, so you may want to check that one for me. But yeah, you can pause this video if you want to jot anything down or think of anything or re-listen to anything. But I'm going to keep rolling. A closed air column. Now again, closed, I know on one of the first slides I drew a column that was closed at both ends, but you can't, it's not really an instrument. So a closed air column means that it's closed at one end. And it says at I'm not even going to have to draw this one, because it says at 2 consecutive resonant lengths, you get to 94 and 156. So you hear loud spots. Those are resonant lengths. Doesn't matter whether it's the first, second, third, or 30th. 94 and 156. The speed of sound is that. Find the frequency of the column. Because the difference between loud spots, or the distance maybe we should say, between loud spots is equal to 1/2 of a wavelength. Distance between these two consecutive loud spots is 156 and 94. So what is that? I believe that's 62 centimeters is equal to 1/2 of a wavelength. So that means a wavelength is double 62, which is 124 centimeters, not meters. Gives me the speed of sound again, says find the frequency, V equals F lambda. The speed is 350. Frequency is what we want to find, and I'm going to change this to meters because I need to. The speed is already in meters per second, so 1.24 meters. Frequency will just be 350 divided by 1.24. I'm doing that in my calculator because I can't do that in my head. And it says that it's 282 hertz. All right, so those are 3 examples that we're using the same concepts, but they're very different, right? Like the first one was from experimental data and using the average distance between loud spots. The second one's very different because it relied on our ability to draw the pattern. And then the third one is actually a lot like the first one, where you have just the 2 loud spots to go off of. But then after that, it's very similar to the first example. So that's going to wrap that up. I have attached questions here. Let me just see. I already had picked these questions out for you. a while ago, and I can't remember exactly which ones I wanted you to do. So let's take a peek right here. Right there. So there is an attachment here, and I just want you to do number 21, 22, and 23. They are challenging, I'll tell you that. So if you get stuck, go ahead and ask, and I can get you started on them. And these are all good questions. I'm just not trying to bombard you with work here this close to the end of the semester, okay? So it'll be probably good enough practice to do 21, 22, 23, but feel free to do them all. I mean, these are all actually very good questions. There's no losers in them, and the answers are right there, so you'll know if you're doing them correctly. Oh, something's just ringing a bell with me right now. I think the very first one. I don't want you to get stuck on it. Yeah. So 19 says 0.48 meters and just decrease the base fundamental frequency. Somehow I believe that that answer is off. Oh, but you're not doing 19. So now I'm just rambling. All right, you should be good. 21, 22, 23. If you're going to try 19 for some reason, I seem to remember the answer is not good for that one. So if you are doing 19, feel free to message me through Classroom in the comments or by email, and I can help you with that one. But the rest of them, the answers are there. You can work backwards if you want. If it's not working for me, get a hold of me as usual. All right, I think that that's it for now. Good luck, guys.